Hello, I'm Jiahua Li. I'm an undergrad student from National Tsinghua University. Today, I'm going to share our paper Idling, Enhancing Memory in Diffusion-based Word Model by Linear Time Sequence Modeling, which has been accepted to NeurIPS 2025 and selected as a spotlight presentation. Model-free ILO is already achieved success in a wide range of tasks. But the disadvantage is that model-free methods need to interact with the environment many times to learn something. In other words, model-free ILO is not sample efficient. However, if we have a good word model, the agent can interact with the word model instead of interacting with the real environment. The word model can generate a lot of experiences, and the RL agent learns from this data. These approaches reduce the number of interactions with the real environment, thereby improving sample efficiency. So, how can we get a good word model in model-based reinforcement learning? We need to learn a word model from the collected experiences. So we can consider this as a supervised learning problem. Learning reward prediction becomes a regression problem, while learning next state prediction is a density estimation problem. We pick a loss function such as mean square error or a KLO divergence, and then optimize the model parameters to minimize the empirical loss. The previous state-of-the-art method, Diamond, which used two independent models to predict next frame and reward termination signals. First, they use EDM diffusion model that condition on the previous 4 frames and actions to generate the next frame through a diffusion process. Second, they use a CNN LSTM network to predict reward and termination signal from the previous information. Although Diamond achieved good results on the Atari benchmark, it also brings two limitations. First, Diamond's diffusion model has memory limitations, since it only remembers the previous 4 frames. Second, the separated architecture causes the two models to be unable to share the word model's hidden representation. To address this limitation, we introduced Idling, a unified word model that integrates the advantage of diffusion models and Mamba state space models. In the memory task mini-grid memory, the agent needs to remember the key object in the room and walk through the corridor. At the end of the corridor, the agent needs to pick an object that is the same as the object in the room. We found that Diamond failed to solve this task due to its memory limitation, but our Idling successfully addressed this limitation. The trainable components of Idling's word model are formalized as follows. First, we have the recurrent embedding module, which processes the observation and action history to generate hidden embedding. Second, the next frame predictor uses these hidden embeddings to predict future observations. Then we have a reward predictor and termination predictor, which both use the same hidden embeddings to predict reward and episode termination signals. In the recurrent embedding module, we use Mamba as a main architecture. We compute the hidden embedding from Mamba's output through recurrent updates. Why do we use Mamba? First, is because of its linear time complexity. It's efficient and simple enough for word modeling. Second, it can remember important information through Mamba's selective mechanism. Finally, it allows parallel training through its parallel scan algorithm. In the next frame predictor, we also use an EDM diffusion model. To maintain short-term memory, we use frame stacking that condition on the previous L frames, preserving fine-grained visual details. For long-term memory, the diffusion model condition on the hidden embedding from REM's output. So, the generation condition can be formalized as this equation. Adeline's diffusion model condition on this information using adaptive group normalization and cross-attention mechanisms. The observation loss is mean square error, which follows the standard diffusion literature. For the reward and termination predictor, unlike Diamond, which use independent CNN LSTM networks to predict reward and termination signals, Adeline's reward and termination predictor shares the same hidden embedding with the next frame predictor, forming a unified world model architecture. In Adeline world model training, the key challenge is to maintain comparable computational efficiency to Diamond while solving the memory limitation. During training, we follow these implementation details. First, we select a trajectory of length t. Then, we use Mamba's parallel scan algorithm to efficiently compute the hidden embeddings for all time steps in the trajectory. Finally, we compute the reward loss, termination loss, and observation loss, and jointly optimize the Adeline world model using all these loss together. Now, let me explain the key insight in Adeline's training strategy for the next frame predictor. Diamond uses a fixed 4-frame window and only requires one diffusion pass when computing the observation loss. However, Adeline maintains completely trajectory memory. If we compute the loss at every time step, it will require t times of diffusion pass, which is computationally expensive. Our solution is to approximate the complete loss through random sampling of a single target time step. We randomly sample J from a uniform distribution within the trajectory, where B represents burn-in steps to ensure the model has sufficient context. Through this approximation, we only need one diffusion pass during world model training, while allowing the diffusion model to process memory capabilities through the REM hidden embeddings. Due to Adeline's unified architecture, we adopt end-to-end optimization during training. We use harmonizers from Harmony Dream to balance the observation loss and reward loss. Why do we need harmonizers? There are two main reasons. First, high-dimensional visual observation and scalar rewards have very different scales. The observation loss tend to be much larger than the reward loss. Second, without proper balancing, observation modeling tends to dominate the learning objective. Our loss harmonization approach uses adaptive weights. The total loss includes these weighted terms plus logarithmic regularization terms. The key insight is that this maintains optimal balance by ensuring the expected value of the weighted loss equals to 1. And here is our complete Adeline world model architecture overview. We use UNet as a diffusion model's backbone for the next frame predictor, showing in the top section. In the bottom left, we have the Mamba-based recurring embedding module that processes observation and action sequence to generate hidden embedding. On the bottom right, we use two simple MLPs to predict reward and termination signals, both conditioned on the hidden embedding from the REM. For agent behavior learning, Edelin follows Diamond's framework to ensure a fair comparison. In the Atari 100K benchmark, Edelin achieves new state-of-the-art performance, significantly surpassing previous methods including Diamond, Storm, and Dreamer v3. To further validate Edelin's war model capabilities, we tested it in 3D environment using Vistum. Edelin significantly outperformed Diamond across multiple Vistum scenarios, particularly in complex scenarios like daily corridor and predict position. Looking at the qualitative results at the top, you can see the visual prediction from Edelin compared to Diamond in the daily corridor scenarios. The green boxes highlight where Edelin successfully predicts important visual detail like enemies and armors, while the red boxes show that where Diamond fails to capture these critical elements. We also evaluate Edelin at Crafter, which tests long-term reasoning and memory capabilities. Edelin surpassed all other baselines while maintaining parameter efficiency. Most importantly, Edelin delivers much better performance than Diamond while using a similar parameter count. This shows the effectiveness of our memory enhancement. We also compared the training efficiency between Diamond and Edelin on an RTX 4090 GPU for Atari 100K single environment training. The results show that Edelin maintains comparable computational efficiency to Diamond. We also conduct evaluation studies on the choice of recurrent embedded module architecture, comparing Mamba with other sequence models. I want to emphasize that exploring better model architecture is not our main goal. Our primary contribution is solving the memory limitation in diffusion-based war model. Mamba simply provides an effective and efficient way to achieve this, but the unified framework we propose could potentially work with other sequence models as well. This evaluation study validates our architecture choice, but the key insight is that integrate of long-term memory capabilities with diffusion models, regardless of the specific sequence model used. We also conduct an evaluation study on the cross-attention mechanism in our next frame predictor. The results show that Edelin with cross-attention outperforms the version without cross-attention. We conduct an evaluation study on the effect of harmonizer in our training process. This table compares Edelin with and without harmonizers across the full Atari 100K benchmark. The results clearly demonstrate the importance of harmonizers for optimal performance. We also conduct the painstaking evaluation study to validate our design choice of using both Mamba hidden state and explicit frame staking. The results demonstrate that both components serve important and complementary roles. To summarize, Edelin makes three key contributions to model-based reinforcement learning. First, Edelin successfully solved the memory limitation of previous methods while maintaining comparable computational efficiency. Second, we propose a unified diffusion war model architecture with shared latent representation. Unlike diamond-separated networks, our unified approach enables efficient representation sharing across all prediction tasks. Finally, Adderall suppressed all baselines across diverse environments, Atari, Crafter, Wisdom, demonstrating the broad applicability and effectiveness of our approach. Thank you for your attention. You can also find our code, project page, and paper through this QR code for further details.